A specialized high-strain steel alloy is liquefied to create a seamless casing capable of housing a three-stage thermonuclear physics package. As the pour commences, the mold begins its centrifugal rotation, a critical process to ensure uniform density and structural integrity. Slowly, the 10-foot-long vessel takes shape layer by layer as the molten steel fills the vertical void. The alloy must be maintained at a specific temperature range to prevent premature solidification during the 180-second pour. At peak rotation, the casing is forged in a crucible of kinetic energy and thermal intensity. With the pour complete, the mold must maintain its speed as the cooling process begins to lock the atoms into a rigid lattice. Controlled cooling is the next phase, preventing thermal shock that could compromise the casing's structural limits. The B41's hull is the thickest of any U.S. nuclear gravity bomb, designed to withstand the immense stresses of supersonic deployment. As the outer skin solidifies, the casing transforms from a liquid mass into a singular ferrous womb. The rough cast surface hides the immense strength required to hold the multi-megaton physics package within. The mold segments retract, exposing the massive 10-foot structure to the factory air for the first time. A seamless, high-strength cylinder, the B41's casing is a marvel of Cold War industrial engineering. Remote-controlled manipulators provide the surgical precision required to handle the volatile core without human exposure. The primary takes shape as a truncated icosahedron, a geometry designed for maximum compression efficiency. Precision rotation allows the manipulator arms to build the sphere symmetrically from all sides. With the final lens in place, the plutonium pit is now completely encased within its explosive shell. A structural tensioning ring is applied, locking the explosive lenses into a rigid singular unit. The initiation harness is introduced, connecting each lens to the firing system. Every lens requires its own dedicated detonator. These must fire within nanoseconds of each other. Precision routing ensures the wiring does not interfere with the aerodynamic or structural integrity of the primary. An outer protective skin is applied, sealing the high explosives from environmental degradation. The housing is bolted to aerospace specifications, ensuring the primary heart remains intact during the B-52's flight. Electrical continuity tests verify that every circuit is live and ready for the firing signal. The primary heart is complete, a masterwork of physics and engineering, ready to trigger the multi-stage fusion process. We begin the fusion fuel stacking process by inspecting the raw lithium, 6-deuteride, the primary fuel source for the bomb's massive energy yield. The raw material is loaded into an isostatic press to be compacted into high-density cylindrical segments. A vacuum-tight seal is established to ensure uniform density during the high-pressure molding phase. Out comes the compressed fuel segment, now possessing the structural integrity required for the physics package. Each segment is machined to sub-millimeter tolerances to ensure a perfect fit within the radiation case. The tamper is fitted snugly around the fuel core, creating the first layer of the secondary stage assembly. The assembly is built upon a high-strength base plate mounted on a precision vertical alignment rig. The first layer of fusion fuel is carefully positioned, marking the beginning of the vertical stack. A central fissile spark plug is inserted, which will ignite the fusion process once compressed by the primary's radiation. Specialized interfaces are applied between layers to ensure consistent energy transfer across the entire stage. The tertiary fusion stages are now added, significantly increasing the total yield of the B41 physics package. The alignment between the two massive stages must be absolute to prevent any asymmetries during the thermonuclear burn. Using laser precision, we verify that the entire internal physics package is perfectly vertical. An internal structural frame is installed to provide the mechanical compression needed to hold the stages during transport. Final torque is applied to the retaining assembly, locking the fusion fuel into its permanent configuration. With the fuel stacking complete, the secondary and tertiary stages are ready for integration into the radiation channels. To bridge the primary and fusion stages, a specialized robotic gantry enters the casing with surgical precision. This gantry is responsible for the delicate task of installing the interstage radiation channels. These channels are the critical pathways designed to guide X-ray energy during the detonation sequence. Once positioned, the channels are secured to withstand the immense pressures of the firing sequence. Next, the lead-lined radiation shields are prepared for installation around the central core. These shields prevent premature heating of the fusion fuel by the initial fission burst. Precision bolting ensures the shields remain fixed during the high G forces of deployment. The interstage assembly now begins to form a continuous bridge for radiation transport. Laser telemetry verifies the geometric integrity of the radiation hohlraum. Every joint is sealed to prevent X-ray leakage into unwanted areas of the casing. The path to the tertiary stage is also reinforced, completing the three-stage physics package bridge. With the tertiary link established, the energy channeling system is physically complete. Thermal insulation is added to protect the delicate physics components from external environmental heat. The gantry exits, leaving behind a perfectly integrated radiation transport system. Final visual confirmation ensures no debris remains in the interstage void. The radiation channeling phase is complete, bridging the primary to the fusion stages. The integration process begins at the rear of the warhead, where the complex nervous system of the weapon lies exposed. Precision robotic arms begin the meticulous task of routing the primary firing cables through hardened conduits. Every connection is critical. The first safety interlock is established with a secure gold-plated interface. High reliability joints are soldered under vacuum-like conditions to prevent any microscopic oxidation. The firing pulse generator, the heart of the electrical system, is carefully lowered into its shock-mounted cradle. Redundant capacitor banks are integrated, designed to deliver the massive electrical surge required for simultaneous detonation. Rigorous continuity testing ensures that the electrical pathways are flawlessly integrated with the primary trigger. The deployment harness for the braking system is now routed toward the rearmost mounting points. A dedicated internal chassis is mounted to house the dual redundant fusing clock systems. Dual fusing modules are aligned, providing the weapon with multiple fail-safe options for airburst or contact detonation. Vibration-resistant clips secure the wiring, ensuring the integrity of the nervous system during the high G forces of deployment. The heart of the braking system, a 40-foot reinforced nylon parachute, is lowered into its housing. High-strength riser lines are shackled to the primary airframe, designed to withstand the immense shock of a high-speed deployment. A final inspection of the pressure seals ensures the parachute will deploy reliably under extreme atmospheric conditions. The raw 10,000-pound steel casing enters the automated finishing bay, ready for its protective thermal skin. Every square inch of the high-strength steel is chemically decontaminated to ensure absolute adhesion of the reflective coatings. Precision robotics prepare to apply the primer, maintaining a perfectly consistent distance from the bomb's curved surface. The first layer of primer is applied, creating a molecular bond between the steel airframe and the upcoming thermal shield. Automation ensures a uniform thickness critical for the aerodynamic stability and weight distribution of the weapon. Even the complex geometry of the tail fins is coated, preventing corrosion and preparing for the final thermal layer. Infrared curing stabilizes the primer, preparing the surface for the specialized white reflective finish. Now the signature white thermal reflective coating is applied, designed to deflect the intense flash of a nuclear detonation. Complete coverage is essential. A single gap in the reflective coating could lead to catastrophic structural failure during a blast. A final high-gloss sealant is added, ensuring the weapon remains pristine during long-term storage and deployment. Quality control verifies the thickness of the shield to within microns of the engineering specification. The fully coated weapon is moved to the environmental test bay to simulate the stresses of high-speed flight. Massive clamps secure the 10,000-pound weapon, preparing it for a grueling vibration stress test. The test begins at low frequencies, simulating the turbulence experienced inside the bomb bay of a B-52. The loading process begins as the heavy hydraulic lift is precision-aligned beneath the 10,000-pound B-41 weapon. The cradle engages, establishing the primary contact points required for the vertical ascent into the stratofortress. Hydraulic pressure builds slowly, overcoming gravity to lift the massive thermonuclear device from its transport carriage. Precision valves regulate the flow of hydraulic fluid, ensuring a smooth, jolt-free movement for the sensitive physics package. As it enters the belly of the B-52, the weapon is engulfed by the dark structural ribbing of the internal weapons bay. Alignment is critical. The heavy-duty lugs must match the aircraft's suspension shackles with sub-millimeter precision. Ground crews provide manual guidance, ensuring the 4.8-meter-long weapon clears the internal bulkheads. With a resounding mechanical strike, the primary shackles lock, transferring the full 5-ton weight to the stratofortress. Secondary locking systems engage automatically, providing redundant security for the high-yield payload. Access ports are open to reach the weapon's internal brains and physical safety interfaces. The first mechanical arming pin is inserted, bridging the gap between the aircraft's release system and the bomb's internal logic. Each pin is physically secured, ensuring that vibration during flight cannot dislodge the weapon's safety configurations. Attention shifts to the flight deck, where the manual fail-safe keys are prepared for synchronization. The insertion of the manual fail-safe key initiates the final handshake between the crew and the weapon. Rotation of the key completes the physical arming circuit, a final human-in-the-loop safety requirement. The final ground safety streamers are removed, transitioning the weapon from a dormant state to mission-ready status. As the bay doors seal, the stratofortress fully embraces the B-41, ready for its long-range strategic patrol. The retarded delivery sequence begins with the activation of the primary hydraulic systems within the B-52's weapons bay. As the doors begin their synchronized opening, the internal environment is subjected to the violent aerodynamics of high-altitude flight. Exposed to the slipstream, the 10,000-pound weapon remains secured by the primary release shackle awaiting the final drop command. The structural integrity of the mounting lugs is critical, holding the massive thermal-shielded casing against the pull of gravity and air resistance. Upon reaching the release point, the electronic solenoid fires, initiating the mechanical separation of the weapon from the aircraft. The mechanical claw releases its grip, allowing the B41 to transition from a payload to a free-falling gravity bomb. Gravitational force pulls the weapon clear of the internal bay where it must navigate the turbulent boundary layer of the B52. As the weapon clears the aircraft, it enters a state of controlled freefall, stabilized by its internal gyroscopic systems. Stability is paramount during the initial seconds of the drop to ensure the parachute system deploys without entanglement. A precisely timed pyrotechnic charge jettisons the tail cone cover, exposing the parachute compartment. The pilot chute is the first stage of the deceleration sequence designed to extract the much larger main canopy. This small drogue chute provides the necessary tension to pull the heavy-duty deployment bag from its housing. The extraction of the main deployment bag must be flawlessly executed to prevent the massive canopy from shredding in the high-speed air. Known as retarded delivery, this parachute retarded mode allows the delivery aircraft to reach a safe distance before detonation. The 40-foot reinforced nylon chute is designed to withstand the immense shock of opening at high subsonic speeds. Full inflation provides the drag necessary to stabilize the 10,000-pound weapon into a slow, predictable vertical descent. As the weapon descends through the cloud layer, the parachute system maintains aerodynamic stability for the calculated delivery. Moisture from the troposphere streaks the specialized thermal reflective coating designed to withstand the upcoming flash. Telemetry systems synchronize with the internal firing package as the weapon nears the designated burst altitude. Ground proximity sensors activate, calculating the precise microsecond required for an optimal air burst detonation. The sophisticated fusing system prepares the firing sequence, initiating the high-voltage discharge to the primary stage. Despite its 10,000-pound mass, the B41 is held in a precise vertical orientation by the drag of the reinforced chutes. As the simulated detonation altitude is reached, we transition to the physics grid to visualize the 25 megaton sequence. The primary fission trigger ignites, releasing an initial burst of X-ray energy through the internal radiation channels. Radiation pressure begins the compression of the lithium 6-deuteride fuel, reaching pressures found only in the centers of stars. Fusion begins surging through the secondary and tertiary stages to reach the full 25 megaton yield capacity. The initial fireball expansion represents the most powerful thermonuclear release ever deployed in the United States nuclear triad. The 25 megaton yield produces a thermal radiation radius capable of causing third-degree burns up to 30 miles away. Spanning over 2,800 square miles, the thermal footprint covers an entire metropolitan area in a single pulse. Following the flash, the overpressure shock wave moves at supersonic speeds, leveling structures within a dozen miles. At 25 megatons, the B41 was the peak of strategic destructive power during the Cold War era. The physics of the three-stage design ensured that the maximum amount of fusion fuel was utilized in the reaction. This visualization concludes the operational assessment of the B41's maximum strategic potential. The B41 enters its final journey at the secure automated dismantlement cell, marking the end of its strategic service. The external casing is carefully breached, exposing the internal architecture after decades of constant readiness. Technicians remotely monitor as the complex firing and fusing systems are systematically neutralized and disconnected. The fissile core is sealed into a specialized vault container, ensuring its stability during the recycling phase. The interstage radiation channels, once designed to focus X-rays, are dismantled and cataloged for disposal. The massive secondary fusion stage is extracted, representing the heart of the B41's multi-megaton yield. Tertiary components in heavy uranium tampers are broken down, finalizing the extraction of all nuclear materials. The massive steel hull is thoroughly decontaminated, leaving behind a hollow monument to Cold War engineering. The parachute deceleration system has removed its heavy nylon fabric, no longer needed for delayed delivery. Permanent markings are applied to the casing, designating it as an inert historical artifact. A final verification scan ensures all sensitive components have been removed and the shell is safe for public preservation. The casing is transported to a high-security national monument, preserved as a testament to the scale of the nuclear triad. The fissile materials are repurposed, feeding into modern warhead life extension programs or peaceful energy research. The B41 remains the most powerful thermonuclear weapon ever deployed by the United States, a silent witness to an era of absolute deterrence.